Hi there. My name is David Bozier. I'm a technical lead at Graphcore, and today I will be giving a very high-level overview of our IPU, our graph compiler, and how we use LLVM under the hood. I'll then give way to my colleague Thomas, who will go into some more detail of the technical challenges and experiences we had whilst implementing our custom backend. So at Graphcore, we provide full solutions that will allow innovators to make breakthroughs in machine intelligence. And we do this by providing a chip we call the Intelligence Processing Unit, or IPU for short. This chip offers 350 teraflops of compute, and it has nearly a gigabyte of in-processor memory, offering memory access of 65 terabytes per second. This memory is evenly split across 1,472 processor cores, or tiles as we call it in software. And there's 6 threads per core, allowing a total of 8,832 independent parallel programs. We can also connect 10 of these together. So yeah, we can see how our IPU architecture differs from traditional CPU or GPU architectures here. One thing to note, our IPU is massively parallel, multiple instructions, multiple data. It has ultra-high, ultra-fast memory access and uses a bulk synchronous parallel execution model, which go into a bit more detail later. So the hardware is only as good as the software that supports it. So at Graphcore, we provide a full software stack powered by our Poplar SDK. We support all of the major machine learning frameworks, or most of them, such as TensorFlow, Onyx, Keras, PyTorch. And this allows users to easily migrate to the IPU platform. So within Poplar, there's 3 main components. We have the graph library, which is an API for building computational graphs and utility functions to help with that. Then we have the graph compiler that maps the computational graph to target the IPU using the bulk synchronous parallel execution model. And then finally, we have this graph engine, which is used to deploy and execute the computational graph on the device. And you can see in the graph compiler at the top there, we have a little dragon to indicate where we use LLVM to generate our machine code. We also provide a more traditional command line style toolchain for internal developers for various projects, such as creating the drivers, but also it is good for us for testing. So all machine intelligence applications can be represented as a computational graph. And there's 3 simple constructs to that. So we have data that is to be processed by the graph, vertices that perform that processing on that data, and then we have the edges that define the communication pattern between data and vertices. So on the left here, we can see an example where we have 4 pieces of data that are connected to 2 adder vertices, which will perform an add. These 2 will do it in parallel as part of a compute set. And the output will be more data. And then we have another phase where we do another add to get the final result. The exchange phase shows the transition of the edges between data and vertices in the computational graph. And the computation phase is the actual execution of the compute. Our software maps this graph to the IPU device using a bulk synchronous parallel schedule. And this model allows us to efficiently execute large computational graph applications on the processor. And then on the right, we can see a screenshot from our PopVision graph analyzer tool. And this shows us the utilization across all of the tiles on our device, so we can see how well we are doing. So in our programming paradigm, we have code for both host and target device. The host program constructs a compute graph by defining and connecting the tensors and vertices, and then mapping them to the tile on the IPU. We also define control programs and compute sets for where we can execute things in parallel. Data is acquired and processed on the CPU, and then streams are used to send it to and from the device. Finally, at the end there, we have our graph engine, which will execute the compute graph. At the top, you can see something called add codelet to our graph. Codelets are what we use to define our vertices. These are the things that we use LLVM for to produce machine code for the device. So we'll take a look at that now. So codelets are written using C++ 17. We've made no modifications to the language, and that really gives users a familiar programming experience, so it's easy to adapt to. We also provide a subset of the C runtime and standard libraries where we can. Some things remain unavailable because we have no dynamic memory allocation on our system. Each vertex is single-threaded and running on a single tile. This simple execution model on the device allows us to easily provide an IPU LLVM backend that takes advantage of all the middle-end optimizations, and it really enabled us to create a backend with minimal changes to upstream code, and we have no modifications to the IR. So by doing that, it's quite easy to maintain and keep up to date with LLVM upstream. So vertices are written as C++ classes that inherit from a vertex class. The fields of the class specify the inputs, outputs, and internal data of the vertex. And there's a single compute method. Compute functions can be written in assembly. We have a number of power users internally that are very intimate with our device. So they insist on writing assembly to get the absolute peak of performance. And so that's a challenge for us to make sure that our code generation can meet the expectations that they have. And we're quite competitive, so we quite want to exceed their assembly-driven code. We do recommend, there are some cases where you do need to drop to assembly. We have an accumulating matrix product unit on the tile, which currently we don't represent in the language or within the IR. So that's something we want to look at in the future. We still recommend using C++ where possible, particularly to keep it forwards compatible with the next generations of our architecture. And we do provide a large number of highly optimized codelets. So the probability is we might have already done it for you. So there are two things that happen when we add a codelet to the graph. The first, we need to do some analysis on the codelet. We do that using libclang, and we use recursive visitors to go through the vertex fields. We do a number of things. We verify that the vertex is well formed, so the compute signature has to be correct. We check that the fields are of a correct type. We use the Poplar library runtimes, where we have Poplar input, output. We use that to identify where we are connecting data to our vertices. This is all done by Poplar. And we do that by creating metadata for connecting this tensor data to the vertex fields. We also need to add a wrapper to create the entry point so we can perform our execution of the vertex. And we do this in C++. So rather than creating a stub of machine code, we actually provide, we pre-process the C++ source to add the additional functions. And then we can make use of the inliner, so this kind of all disappears. the bottom we can see that wrapper source code. A couple of interesting things there. We mark it as a worker, which is what we call the threads that run on our tile. And secondly, we add another attribute, Colossus Vertex, which indicates that we're going to use a different ABI calling convention. So the supervisor thread will call this function, and we expect it to kill the thread and return to the supervisor when it's done. So after that, we do the compilation and we have our binary machine code, and then we need to load it on the device. So once the graph builder has compiled all of the vertices and all of the variables, edge, compute sets, and programs, we are ready to create our binary image and load it onto a tile. So to start off, we simply add the vertices that we've compiled and our tensor data. Then we need to create some control code that is responsible for spawning and running the worker threads and executing these compute kernels. This main thread is called the supervisor. It runs slightly differently to the workers. It doesn't have access to the floating point unit, but it performs operations for exchange of data and running threads. This code is automatically generated by Poplar under the hood, compiled, and then added. Then we need to add the exchange code for communication across tiles. So that's more code that's generated under the hood by Poplar. And then finally, as we do provide runtime library functions, we might also need to link those in as well. So we repeat this for every tile on the device, and then we deploy it to be executed. We used to use LLD for this process, but we found that it didn't scale too well once we were going for bigger applications. We also have some interesting memory pattern access patterns. So Poplar knows more about the data and the more optimal way of laying it out. So we ended up providing our own internal linker. So that's it for my part of the talk, and I'll hand you over to Thomas to go over some of the specifics. Oops, sorry.
So for the remainder of this talk, let's explore some of the aspects that make the IPU unique from LLVM's point of view. So IPU tiles are superscalar and have two instruction pipeline, main and aux. The pipeline is strongly associated with the register file being used. So instructions that execute on the main pipeline or those who use the main register file or MRF, such as arithmetic operation and load and store instructions. Floating point operation execute on the aux pipeline because they use the aux register file or ARF. It is possible to copy values from one register file to the other, either by using the A2M instruction to copy from the ARF to MRF register file, or by spilling to the stack for copying the other way. One particularity of the IPU is that it possesses floating point. It possesses bitwise operation that can operate on both pipelines, so main and aux, and thus on both type of registers. That begs the question on how to take advantage of this to avoid copy between register file. Without going into too much details, here are some of the key ideas of the placement algorithm. So each node in the selection DAG will have a pipeline preference, which is main, aux, or either. The pipeline preference is a function of where it can execute, but also the preference of its operand, so it's a recursive property. And then when looking at a given binary operation, we'll make a vote based on based on the preference of the operand, and also where can the operation execute. So we have an example here where we have some bitwise operations, so complement and AND. Initially the IO will be converting all of that to integer, to integer type. So so that we can do the bitwise operation. And then we can see that all these bitwise operation can execute on both pipeline, and we can avoid the bit cast if we change to execute on the aux pipeline. Right. So compared to typical desktop systems or server systems, the IPU runtime environment has some important differences. It doesn't have an operating system, so it's like bare metal. This is handled on the host side. But also doesn't have dynamic allocation. It could have, it's just for performance reason to better utilize memory and also to be able to, at compile time, determine whether we'll have enough memory. And each tile has only about 600 kilobytes of memory. So the C++ freestanding proposal will address the first aspect, but we'll have to deal with the lack of dynamic memory allocation. So we needed to do a lot of changes in libcxx to handle this. What we did is we don't use all of libcxx, but only features that our developers tells us they need to reduce the burden. We needed to do lots of changes to the random include to reduce the memory usage of all the components to fit within the memory. We also needed to remove some of the pseudo-random number generators because they were using dynamic memory allocation. And we had to adapt some of the predefined value also to increase the quality of the numbers that were generated while still keeping reasonable code size. Some other change we had to do is for the test suite, we had to change a lot of use of std vector by std_array. And we had to look at all the dependencies between headers to try to, whenever we want to bring a new functionality, to not pull in too many headers at the same time. Because then they also need to be modified. So one way to manage this complexity was that we make a copy of the libcxx code into a separate repository, which allows us to merge from upstream less frequently compared to the rest of the LLVM code. As my esteemed colleague Yannick presented yesterday, we have the IPU support hardware loops. The hardware loop to be able to generate hardware loop, we need to guarantee that the trip count will be within given bounds. We try to use built-in assume, but in some cases it won't be able to propagate the information, and we still won't be able to use hardware loop instructions. So one thing we've done is we've used bit int, which allows us to define an integer with a lower number of bits than the typical int and short, etc. But this doesn't compose too well with when we do operation with other integers. So we created a wrapper around bit int, so basically a structure that contains a bit int value inside, with lots of overload and template magic to be able to do any kind of operation with other integer. Comparison, addition, etc. Our toolchain also has support for. So we also have support for the IPU in the toolchain for the debugger. So as Dave mentioned, the IPU is composed of many tiles. So how do we manage this in LLDB? Well, the LLDB supports multi-process applications. What we do is we pretend that every tile is just one process, which will allow us to execute, to run the application, the whole IPU application. So we have added several commands to LLDB, global command to continue interrupt, and also some command to manage 1,000 threads, and for instance list the threads, etc., with information that's more interesting than the standard command. We've had quite some positive experience with LLVM. Lots of, obviously we've took advantage of all the middle-end optimization and C++ support. We were able to use successfully the bint-int feature. And built-ins, lots of built-ins worked out of the box with just being able to lower it. And we've used also pragma and attributes for loop unrolling on no inline that works. And so it was quite good. And we also had good experience with working with the community when we reported the patch to fix some issues. They were usually dealt in a timely manner, and people accepted patch when they were reasonably small and didn't create too much maintenance burden. We plan to open source our backends. We actively work on it. It will be available soon. You'll find it when it's available on our GitHub page, where we also have other open source aspects like the poplibs library. We'll send a message to the discourse once this becomes available. Thank you.
Awesome. Thank you, David and Thomas. Do we have any questions?
Hello. Yeah, it was very, very, very interesting, this talk. Thanks. My question is maybe a naive one, but have you ever considered using, because basically you use C++ and then LLVM IR, so C++ is sort of an intermediate representation from Python to LLVM IR. Have you ever considered using something more hierarchical like MLIR instead of C++?
Yeah, so we've been around for a while, and we were one of the first chips dedicated to solving this space. So at the time, that technology wasn't available, and we were trying to get something available first. So the decision behind coming up with what we have, that's the reason. However, we are looking into those things. We're possibly not quite ready to kind of present where we are with that. We have a few engineers that are here today that are working on it, and if you look at the lanyards with Graphcore, they might be able to give you some more information. So to answer your question, it is something we're looking at, yes. But the reason it's not something we're actively using is because we built the technology before that was available to us. Right. So
okay. Makes perfectly sense.
Great.
Thank you.
Any other questions?
Thank you. Very interesting. I'm wondering if you know of any audio application of this technology, because in audio processing and DSP processing, we have very specific needs. In particular, we don't have many data parallelism, and as often we have recursive dependencies. So I understand that your graph is actually only a DAG. You don't have cycles in the graph, right? And the cycle should be in the nodes, basically. So my question is, do you know of any application of your technology to audio processing? And do you think it would be adequate?
No, I don't know any application, but I don't see why not. I mean, the architecture is quite generic. All the tiles, the instruction set is quite similar to typical CPU, and yeah, you just have many of them. So the main limitation will be memory, but yeah, you should be able to execute more than machine learning workload on it.
yeah, we do have initiatives where we're trying to look outside of the space for further applications. I think there's an academic program to look at sort of more kind of native development. So, but that's quite a new thing. I don't have anything in particular to announce on that yet.
For example, how fast do you communicate between the CPU and the IPU?
I believe we can find someone who can answer that for you.
Okay.
I can't. I don't have exact numbers for that, I'm afraid.
Fantastic, thank you. I think we have 1 more minute for questions if somebody has a really quick one. If not, then I think we can all thank the speakers. Thank you.